just to remind you that the first midterm for this class is this Friday in class, 50 minutes-ish. It shouldn't be time pressure, but there'll be a few of you who are here at the 55 minutes in or maybe a little after. First people will be done in way half that time. It's 30 questions, multiple choice, same as I do every year, have for a number of years. You can find old exams on the website for this class, and I very much encourage you to take the old exams. Don't just look at the answers, actually take them. It's a different experience. And partly that's to learn what kind of questions I ask, partly you learn from the questions. You should be able to find the right answer, and you should be able to find the 3 wrong answers. Unless I mess up, there are 3 truly wrong answers, not the best answer and the next best answer. I try not to ever have that in the questions. What else? They'll go through everything we've done up until including Wednesday approximately. So I'm probably not going to get much farther than xerographic copiers. So in all likelihood, the test will end with material from xerographic copiers. I'm going to try to cover enough today to make sure that you can do the problem set that's due on Wednesday. We're close. I've done a lot of the things that show up in that problem set. Any other questions about the exam? It's a Scantron. You'll be filling out a Scantron, so bring a pencil. The scanner does not see pen. It's color sensitive. It's looking whatever color it's using looks right through blue ink and sees nothing. All right, so please bring a pencil. That's about it. Okay. So where we left off last time, approximately, I went off and started playing with this what's called a Van de Graaff generator, which accumulates a really large amount of static electric charge, and therefore very high voltage, which is something I want to come back to. So people were coming up during class and after class. Some people's hair is standing up, other people's not so much. 2 things that people noticed as they're doing it, and you can do it after class again today, is that if you've got anything, you feel sizzles around you. Any sharp point, as we'll see today, part of the thing I want to talk about today is sharp points send charge out into the air. This is the principle behind a lightning rod. And so that's, you can feel the charge. You can feel the sizzle of that charge leaving through sharp points. So people who had sharp stuff on them by accident or otherwise had trouble accumulating charge. And this ball, we have to keep it clean, because if it picks up a little piece of stray conducting stuff that's sharp, it loses its charge. What else? Oh, the other thing was that people were noticing static cling, that when they'd get charge on them, and not only would their hair go up, but various parts of their clothing would sort of grip them. And that's, I think, an example of the polarization effect that's holding the balloon on the screen. Remember the balloon on the screen? I'm not sure it's been there all weekend, or whether somebody recharged it and put it back up there. But hopefully you understand the idea of that polarization effect, that if you put a charged object near a neutral object, an object that has no charge on it, they will attract. This effect's always attractive. The charged object polarizes the neutral object. It shifts the charge around in the neutral object in such a way that the charged object is drawn to that polarized surface. Any questions about the polarized surface? I talked about it last time, and I'm happy to talk about it again if it's a puzzle. Yeah? Are they transferring energy? They're not transferring energy, well, energy is messy in this story, but they're not transferring charge is probably what you want to ask. The charge, that balloon has the only net charge. It's the only charged object, the one that has a non-neutral charge. The screen, in principle, is still electrically neutral, but what's happened is its positive and negative charges have shifted relative to one another, so that it has a positive-ish end and a negative-ish end. It happens in this case, the balloon, as I said last time, the balloon picks up a negative charge from, like, your hair, for most things. It's not, yeah, so it has a negative charge. And it draws the positive charge in the screen a little closer, and it shoves the negative charge in the screen a little farther. So the screen now has a little bit of a positively charged surface and a negatively charged back. Is that okay? All right. So what I sort of leapt ahead to go talk about that funny Van de Graaff generator was the idea of voltage. That's where we were. And if you have two charged objects near each other, so we'll set aside the polarized stuff, which is fun, but not the story at the moment. If you have two charged objects, so, okay, I can start using my toys here. So I've got a positive object and negative object. When they're close together, they're relatively happy. I mean, ideally, they would like to be on top of each other and there'd be no charge, just gone. If they can't do that, so for example, if you've got a sock and a shirt, neither of which is able to let the charge truly move and cover up the other one's charge. So you've got a sock and a shirt. I don't know which is which. Doesn't matter. And they're very close together, one positive, one negative. They can sit there like this. If you pull them apart, and it does take pulling, they don't like being pulled apart. They attract each other. So this process, what I'm just doing right now, pulling apart at constant velocity, if you will, that takes work. I'm doing work pulling them apart. That energy goes somewhere. It doesn't just disappear from me and go into nothing. It went into the charges, and it's now stored in the forces between these two charges. They're attracting each other. They would love to get back together. If I let them, they would do it. Okay? So I've torn them apart, and the energy now is in them, and the force between them. The energy per charge has gone up. The energy has gone up, I should say. And in particular, for this positively charged object, the energy associated with each portion of charge in this object, each coulomb, which is the unit of charge, has gone up. And we measure, we name the energy per charge. So it's joules is the unit of energy, and the unit of charge is coulombs. So joules per coulomb, energy per charge, is known as voltage. So you've heard of voltage your whole life. This is what voltage actually is. So an ordinary battery, typical batteries are, let's say, 1.5 or 3 volt or something like that. What they're saying is that those batteries are capable of giving each unit of charge, each coulomb of charge, about 3 joules of energy. 3 joules per coulomb is 3 volts. That's a 3 volt battery. We'll talk more about batteries later on, but it gives you just an idea of batteries typically provide these small voltages, small energy per charge. The electric power lines coming into your house give the charges more energy per charge, more voltage. You've probably heard them talked about as 120 volt or 110 volt. I'm not even sure what the standard is in the United States. It's one of those two, or close. And then there are high voltage transmission lines, which we'll talk about later, that have hundreds of thousands of volts, meaning every unit of charge has hundreds of thousands of joules of energy associated with it. All right, so when I pulled them apart, if this was an entire coulomb of charge, and this is an entire coulomb of negative coulomb of charge, and I pulled them apart, and suppose I did 100 joules of work on them, then, I will get myself in trouble over a factor of 2. Whether this guy's got now 100 joules per coulomb, and this guy, so that's 100 volts, and this guy has 100 joules, but it's a negative coulomb, so it's 100 joules per negative coulomb, that is minus 100 volts. The factor of 2 is I'm not sure there are 2 of them. Are they sharing that 100 joules? I'd have to think more carefully than I can do while I'm holding 2 charges in my hand. All right? The point is, you pull them apart, this one goes to positive voltage, being a positive charge. And this one goes to negative voltage, being a negative charge, being a negative amount of charge. It's got energy, but it's energy associated with a negative charge. That's a negative voltage. Is that okay? So these voltages you've heard tell about your whole life, they tell you how much, if you go to a place, if you find a location that is 1,000 volts, what that's saying is that every coulomb of charge that's at that location can release 1,000 joules. if it goes to a place where the voltage is zero, there's no energy per charge. That's another story. Where would you find such a place? The Earth is pretty much that kind of place. So if you've got a place that's 1,000 joules per coulomb, that is 1,000 volts, and you let a coulomb of charge leave there for the Earth, it will probably release 1,000 joules of energy. All right? Any questions about voltage? The idea of voltage. It's not trivial. We'll circle around it a couple times. The other observation is that pulling charges apart raises their voltage. The positive charge goes to high voltage, the negative charge goes to low voltage. And this is why, to an extent, why when you pull clothes apart coming out of the dryer without the dryer sheet, snap, crackle, pop, the act of pulling them apart increases their energy per charge, their voltage, and they can do things now they couldn't do before. For example, make a spark. And that is really the story. So I want to do it like this. That's the story behind this device. What it starts with is just a little bit of electric charge, positive and negative, very close together at the bottom. Down in the bottom, it's got a big rubber band, rubber belt. That's all that's living inside this plastic pipe, and a motor that moves the belt. At the bottom of the pipe, they bring two surfaces very close together, so they fight unequally, as is typical of two chemically different surfaces. They fight unequally over charge, and the belt ends up. It's a little more complicated than that on there, but not much. The belt ends up with a little bit of negative charge on its surface, just like the balloon. Same thing, rubber. And so it ends up with a little bit of negative charge, which, because the belt is moving, it carries up to the ball, and it gives to the ball, and that's another story we have to sort of flesh out. The ball ends up with that charge, and the belt goes back down without any. So the belt keeps carrying negative charge up onto the ball, leaving it behind, and going and getting more. And pretty soon the ball has accumulated a whole lot of negative charge. Well, the act of pulling negative charge from down here when it was near some positive charge and very happy, and pulling it up to this ball, which is already covered with negative charge, that act of carrying it takes work. The belt is carrying charge against its will, essentially, dragging it away from positive charge that it likes and shoving it towards negative charge, which it hates because it's like charge, it doesn't want to go there. And that means it's doing work on the charge, it's adding energy to it. So the charge, as it piles up here on the ball, has more and more and more stored energy, stored in the forces between charges, and therefore electrostatic potential energy. So the voltage is going to a big value. Again, because it's negative charge that's accumulating all this energy, it's going to a very large negative voltage. So this thing goes to like probably minus 200,000 volts. That's about that. You let it go for a second. Okay, now it's at about minus 200,000 volts now, and the negative charge on it is just mad as can be. It wants to go away. So if I put my hand out here, it's hitting my hand. I don't know, can you hear the snap? That's my knuckle. For some reason, your knuckle doesn't care as much. I mean, yeah, I feel it every time it snaps at me, but it's not too bad. So the charge is going, it's also shooting through my shoe into the ground. It's trying to get away. The negative charge can release its energy by spreading out. So it's spreading out first onto me, which is already a really good thing as far as it's concerned. And then if it can do better, it goes into the ground. It went into my shoe and then into the floor. Turn this guy off. Gets snapped at all the time. All right, so you understand, at least in broad brush, how that static generator works? Is that okay? You do something, yeah, Marie? So that's negative voltage. Would it behave differently if it were positive voltage? You probably couldn't tell the difference. It's just so maybe it's my compulsion to have to admit that it's negative voltage in there, because it is, but you could make a Van de Graaff generator that worked with positive voltage too, that carried positive voltage up, piled it up there, and it would be really tough to tell the difference. John? Am I neutral? You tend to be pretty neutral if you've been in contact with something recently that is in contact itself with the Earth. So right now, I'm probably not totally neutral. And actually, I should point out, a device that can tell whether you're neutral or positive or negatively charged, there are many kinds of devices. One of the simplest ones is known as an electroscope. It's this device right here. And all it is an insulated, and we'll talk about what insulated means. Insulated, you have some sense already, is it doesn't conduct electricity. It's sort of an isolated object that has a little metal vein in parallel to another vein. Let me touch it and see what. It moved, actually. Can you see the vein moving? That little vein can get charge on it, and so can the support for it. And when the two of them have some amount of charge, they repel, because it's light charge. So if it's positive, they repel. If it's negative, it's repel. And so evidently, I did have some charge on me. So when I touched that, my charge left me to spread out more. Charge loves to spread out. So I touched this. This is electrically conducting. It put charge out on those two veins. One's fixed, one's able to rotate. And the one that rotated. So evidently I had charge. But if I go and touch something that's connected to the ground, this is probably pretty safe. There's a whole lot of electronics here that's probably electrically grounded. I killed it. I was electrically neutral. What little charge was left on that went onto me, and it's gone, nothing left. So when I was touching the ball, then I was accumulating a lot of charge, but it was going out through my shoe into the ground here. The ground is by and large not conducting too, but it's got metal stuff in it. It's like it's concrete with rebar in it, metal rebar and all that conducts. So I was probably sending charge out into the various conducting parts of the floor and not accumulating very much. That's why when you do what my kids used to call the hair stand-up machine. Stop biting me. Yeah. Right now, the reason I'm standing on a plastic stool is to get me off the floor so that the charge doesn't keep shooting out my feet into the ground. Yeah, I actually do pretty well these days. Yeah. Yeah. If I touch this thing with an electrical conductor, so here's a piece of metal. I can come out here. So it goes through me. It goes through the metal. So the metal. So what electrical conductors, what actually defines an electrical conductor, is something through which charge can move. This is really pushing the limits because this thing, there's so much voltage here, it can push charge through things that aren't supposed to be conducting, like the air, right? So, but certainly a piece of metal can do it nicely. On the other hand, a piece of plastic, well, I mean, I'll go more extreme. A piece of plastic might pull it off, but the problem is the voltage is so outrageous here that even a piece of plastic probably won't do. I won't do it because it goes right through the air and gets me anyway. I'm a glutton for punishment. There was a time when I was in high school. Yeah, I got to tell you the stories. I did a lot of electronics when I was a kid. Earlier, I did a lot of chemistry, which is why I can't smell it. That was a pretty good spark. Anyway, in high school, I was trying to ring the bells in the high school. In the high school, the whole bell system for the high school was operated through the electric power line. They did something to the power line that caused a tone to transmit on the power line that caused the bells to ring. And you could hear the tone in certain rooms that had the right kind of lights. You'd hear the light whistle, and it'd go dee, 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 and then the bell would ring. So I was going to ring the bells, right? And during that afternoon of trying to build up the electronics to do this, I shocked myself so badly, so many times. I was just sort of like, I was just kind of just twitching. Never did ring the bells. All right, I'm going to, hit me one more time. Okay? So, do you understand why we have to stand on stools to use that gadget? So you really can accumulate the charge and be part of it. I will show you just in advance. Yeah. All right, glutton for punishment. So it's really snapping nicely here, right? Sharp point. You think if I go up there with a sharp point, is it going to hit me from farther away, the same distance, or not at all? How many think it's going to hit me from farther away? How many think it's going to hit me the same distance? How many think it's going to hit me not at all? Okay, there's a slight majority, I think, for not at all. Here we go. Ready? It's actually not at all. This thing is killing it. This point is ruining the behavior of the static generator. I'm getting sparks shooting out my toes into the ground, but otherwise nothing up here. And this is the principle behind a lightning rod. Again, Ben Franklin. Remember Ben? All right. Yeah. I had a lot of electronic. Yes. Other things we'll bring out later. The principle behind a lightning rod, which isn't, it's not just to direct the lightning safely from a place that sort of a designated hit-me spot on your house. Lightning rods, if used widely by everybody in a community, they all have these pointed lightning rods, it actually discharges the clouds. It ruins their ability to accumulate static electricity so they don't hit anybody. So one of Ben Franklin's great challenges when he was trying to get people to start using lightning rods was to go past the first couple people. Because the first person who started using lightning rods, they got hit. Hopefully safely. I mean, it would hit the lightning rod and this massive spark would dump all its charge into the ground through a wire. But that wasn't so fun. You don't really want to be the only lightning rod in town. But if the whole town adopts lightning rods, they ruin the spark. No sparks at all. Does that make sense? A little bit? Okay. All right, what I want to do. Okay, so we've talked about voltage. Hopefully you got a sense for what voltage is. At this point, I've already done this. If you take two surfaces, and one positive and negative, and pull them apart, the voltage of the positive one goes up, the voltage of the negative one goes down. That is the story. Okay. Electric conductors, I've told you about that a little already. Let me just finish the job here. So, having told you about this gadget known as an electroscope, there are other devices like this, but I like this one because it's easy to understand. It's not magic electronics. An issue with this semester is that there are a number of demonstrations I can do for you that involve bringing out unfamiliar electronic gadgets. And what's the point? Having a gadget show you something. At this point, you can make an app show you anything. It can show you virtual reality that's wrong, anti-gravity. You can be king all of a sudden, or queen, or anything, or not gender identifying. Anyway, I'll stop. So this, you can see this thing is very good at showing the presence of charge. For example, charge that I had managed to accumulate on this Teflon rod by bringing it into contact with the silk. So this was covered with negative charge. I put it all over that ball. It consequently ended up on the vein of the two veins of the electroscope, and they're telling you, hey man, there's lots of charge around here. I could show you that the other ones, that acrylic rod gets positive charge by taking this charge off. And again, if I let it go onto my hand, of course, a lot of it leaves. I was pretty close to neutral, so it is all left. The last thing I touched over there was the box, which is connected to the earth. All right, but now having shown you that, I can go back and redo. Where'd the plastic? Yeah, I know about you. All right, there's metal. And this was all full of charge from last time I used it. All right, I got to go get rid of my charge. Now I can get rid of its charge. I'm still getting rid of charge. I'm close to 0. We'll call it, yeah, Rachel? Does it behave differently for positive or negative charge? I probably should just show you. It should look pretty much the same. So this is negative. Here's negative on this stuff. That's negative. And over here, I can get positive. And as I bring positive over, this should allow, initially it should allow the electroscope to settle. Actually, what I've done so far is I've polarized the electroscope. I haven't actually transferred charge to it yet. Now I'm transferring the charge. And it's now, it should be covered with positive charge, but I'm having, this is less effective than Teflon. Teflon gives you a wonderful negative charge. Acrylic, you get a modest positive charge. Okay? But it looks the same. But you can figure out which it is by going to one that you know and seeing, does adding a little bit of this known charge cause it to deflect more or less? Other questions? All right. Where I went off was this metal, and now I'm going to go back to Teflon. Metal is an electrical conductor. The whole idea of a conductor is that it allows electric charge to move through the material. That is not a trivial thing to have happen. For charge to move through that material, as we'll see when we start looking at materials and metals and insulators and things in between, for the charge to move, there have to be mobile charges, that is, electrically charged things inside the solid that are capable of moving long distances, that are not held in place. And a lot of atoms and their electrons are held in place. There's nobody that can move. For example, a big chunk of salt or a window, a glass window. There are charges in it all over the place, and they can move microscopic distances, so they can polarize and they can have that balloon stick to them. But they can't, the charges can't move long distances, so they cannot conduct electricity. For example, a piece of plastic. So here's a piece of plastic. I can put negative charge all over the top of that plastic. It's there. I'm sprinkling all over. But it can't do anything. It can't get down to the electroscope to do anything interesting to the electroscope because plastic has no mobile electric charges. They're all there. They can't move. So we'll learn later on how charges are actually able to move through metals and things like metals. All right? The last thing to show you is associated with this question, and it's also important to the Van de Graaff generator. If you put electric charge in a metal pot that is suspended in the air, where will the charge be located? So a pot like this pot, suspended on plastic, which is as good as being suspended in air. If you put charge on that, where is it located? How many think, so the question is inside the pot, outside the pot, or both? How many think it'll be inside the pot? How many think it'll be outside the pot? How many think it'll be both? They're probably 50-50 for outside or inside and outside, both. Okay? So let's try it. Let me get rid of the fun decorations there. So we're going to use that electroscope as the detector for where the charge is. And first, let me put the charge on. It happens to be negative, but who cares? I'll sprinkle it all over. Woo. Go to town. Okay. Lots of charge on that pot. Okay. So let me go and look for it. First, I'm going to, with this, so this is just a transfer ball. It's also isolated. It's on plastic. Just a ball. And right now, it should have no charge on it if I'm lucky. Yeah, no charge on it. I'm going to go look for charge. And first, I'm going to go into the pot, right down the center, and scout out any charge that's on the inside. Okay? Nothing. Okay? How about the outside? Don't you like demonstrations that don't work? All right, try again. I heard a snap, which was not a good sound. I'm not sure where that, who sparked, but somebody sparked. All right. First, we'll look inside. Nothing. Now we'll look outside. Yay! Physics is saved. I had a postdoc that used to say that. When the experiment that was suddenly not working started working again, hey, physics is saved. The charge is on the outside. And that shouldn't be a big surprise because that pot is metal, which means the charge can move through it. And if you put charge everywhere in the metal, it's going to repel. It's all the same charge. And the charge, if it's every charge for itself, the charge is going to do its best to get as far away from all the other charges as it possibly can. If it's on the inside of the pot, it can do a little better. It can go through the pot to the outside. It gets a little farther away, and that's enough. That little better that opportunity to get a little farther away allows the charge to reduce its total potential energy. So when you have a metal object, the charges that you put anywhere in this will tend to go to the surface, the outer surface, because that's the best they can do to spread out and get as far from one another as possible. And that's why the big ball, the Van de Graaff generator, that's why it accumulates the charge. The rubber belt brings the charge into it near the center and lets the charge out. And that charge, being the same charge as it is already all over the ball, goes, I'm in a bad place. I'm near all this other negative charge. What can I do to get as far away from it as possible? Go to the outside. So it rushes to the outside of the ball, and once it's there, it can't get back in. So this device keeps working because the charge keeps going to the outside of that ball and piling up there. And once it's done that, it can't get back. And the new charge comes and joins it. And it keeps on piling up. The only thing that limits this from accumulating the vast amount of negative charge is the sparks. Once you turn it on after a couple of seconds, it's just snapping away because the charge just leaps down, for example, to the bottom. But they do make Van de Graaff generators that make millions of volts. This was, years ago, this was the classic way to make just fantastic voltages. You can do better now, but for a long era, it was hard to beat a Van de Graaff generator for just sheer crazy voltages. All right? This, incidentally, when you're in a lightning storm and they tell you your car gets hit by lightning or something, I don't know. If your car were to get hit by lightning while you are in it, you're probably pretty safe. This is not good for your ears because it's a big kabang, but the charge will tend to stay on the outside. During the actual hit, it's more complicated because the charge is moving, but the charge at equilibrium, given an opportunity, will settle on the outside of things, not where you are. So this is why you want to stay in the car. The last thing you want to do is actually step out of the car and form a conducting circuit from the car to the ground. That's a pretty bad choice. But if a power line falls on your car, for example, fine, stay in the car. The charge is all on the outside. Do not step out and, again, make a contact with the ground. Bad idea. All right? Any other questions about static electricity? Yeah. If you stay in the car, what would take the charge away? If a power line lands on your car, for example, so the power lines have this strange characteristic, as we'll see shortly, of putting first positive charge on your car and then negative, then positive and negative. They change the charge 120 times a second in the United States. That's the alternating current you've heard tell of. And that charge, so the charge is going on and off. And at any given moment, there might be a certain amount of positive or there might be a certain amount of negative. It won't keep getting bigger or smaller, it just keeps on changing. And what you don't want to do is become part of the path for it to go somewhere. So stay inside until somebody comes and rescues you. I mean, if you're totally stuck, you can jump, literally jump. You don't want to be in contact with the car at the time you're in contact with the ground. You want to leave one, be in the air, carrying a small amount of charge with you, and then land. Then you're safe, in the case of a power line. The most extreme example I could think of was during the era of the Berlin Wall and people trying to escape from East Germany. There were episodes where people would escape by way of the power lines that would go over. And so they would go from pylon, the stories would be, they're on high voltage power lines, which are really, really nasty, dangerous, because then you can make a circuit by accident. We'll talk about circuits soon, but you don't want to make a path for current, for charges to move through. So they would go up high and jump onto the wires, so they're not in contact with the pylon at the same time they're in contact with the wire. They would jump onto the wire. They would then do the trip to the next pylon. They would then drop off the wire onto the pylon below. So again, they weren't in contact. And you got to be like, they want to be this far apart. So it was a huge ordeal. Every pylon they would drop off, climb up, drop onto the departing wire, and continue on their way. An example of something not making the jump properly is squirrels, which occasionally, you watch squirrels use the wires as highways in the sky, right? This is fine as long as they don't connect the wires to one another or to a metal connection to the ground, and occasionally they do. And that's, the lights flicker for a second, and then they come back on, hopefully. That is a squirrel becoming a flashbulb. Sorry. It's very sad. Lost opportunity for our doggies to chase them. All right. Any other questions? Okay. I do have at least one more topic to deal with for the problem set to really cover. I want to make sure I get across this. Zero graphic copier. So now this is a real device that you're familiar with. These are the copiers. Just like, okay, Xerox used to be the company that made them, but they're now everywhere. And generically, they're known as zero graphic copiers. They are also laser printers. Laser printer differs from a zero graphic copier only in the source of the image. If a zero graphic copier, the image is written with optics looking at a document. With a laser printer, the image is written for the first time with a laser on a photosensitive surface. But zero graphic copiers are all about static electricity and the control of static electricity. So I've, to an extent, given away the story. If you're covered with static electricity and you hold a sharp pin as you reach out toward a doorknob, if no pin, you reach out the doorknob, snap, you get a nice spark and shock. If you reach out with a pin, how's that going to affect the spark and shock you get? Okay, the question? How many think it'll make the shock you get worse? How about make the shock weaker? How about unchanged? Yeah, weaker. It kills, it ruins your ability to accumulate charge, because that sharp point does an amazing job of spraying charge into the air. And that's a major part of the story for today. The zero graphic copier, I'll give you the basic idea of how it works. Not quite yet, very close. But the key thing that the zero graphic copier has to do is to apply a nice coating of electric charge to a surface that does not conduct electricity when it's in the dark, but that does conduct electricity when it's in the light. So some observations about copiers. They consume colored powder known as toner. So when your laser printer or your copier starts to run dry, you have to go get another toner cartridge. What is that thing? The toner that you're purchasing is a very, very fine, basically a dust. It's mostly a plastic dust with color in it. And it clings to things that are charged, either because the toner itself can be charged or because of polarization effects, like that balloon. So the toner will cling to things by way of static electricity. It does not itself conduct electricity. So the zero graphic copier's job is to move that toner around, apply it where you want it, not apply it where you don't want it, and then fuse it into the paper by way of heat or pressure or both. It used to be that you would pull out copies and they would be clingy to one another, particularly plastic copies. But that's sort of gotten to be dinosaur stuff. You probably have never noticed that the copies can be clingy. So you would have no indication that static electricity had anything to do with them, but it does. The technology, as technology advances, you lose all these hints that something interesting is going on. Like copies don't come out warm anymore, as to my memory. They don't come out clingy anymore. Like they're spoiling all the fun. Okay, so the first question is, how does light arrange colored powder on paper? And this is the basic idea, and then I have to flesh out the science behind it. The basic idea is that the copier is using light to control the presence of static electricity, that is stationary charges. And it coats a surface. The surface that's important is a surface that is known as a photoconductor. Photoconductors are also known as semiconductors. These are materials that are in between electrically conducting and electrically insulating. And in certain circumstances, they can conduct electricity. In other circumstances, they can keep charge from moving. So they're somewhere controllably in between plastic and metal. Okay? And if you have a big wide surface, a very thin layer of this photoconductor on a metal surface, you can sprinkle one charge on the top surface, on the open surface of the photoconductor. The surface is not in contact with metal. You sprinkle charge onto that surface. The presence of that charge will attract the opposite charge onto the metal surface, but they can't get together. So if you sprinkle negative, in this drawing I got up here, some crazy process has sprinkled negative charge onto the top surface of the photoconductor. This is a big plate, big wide surface, very thin, but extensive. It's got negative charge sprinkled onto the surface that's in contact, that touches nothing, it's in the air. On the back surface, a positive charge comes in to match the negative charge. That back surface is metal, so charge can move freely in it. In fact, it's touching the earth. So charge can come wandering in from great distance to get near that negative charge. And in fact, the negative charge has polarized the metal and the earth, which are a big system. The metal and earth are together. They're a pair. And what the negative charge has done, it has attracted positive charge close to it, because positive charge loves to snuggle up near the negative charge. And the negative charge has repelled negative charge away from it. Well, because this metal surface is in contact with the entire earth, the negative charge can get really far away. It can go all the way to the other side of the earth. So it's over there in Australia or something like that to compensate. So this negative charge has polarized the metal and earth, pulling the positive charge here close by and shoving the negative charge, a corresponding amount of negative charge, to the other side of the earth, far away as it can get. And there it sits. The charge sits there in the dark. It'll stay there for a long time. But if you expose parts of that photoconductor to light, either from a document that you put in, your transcript while you're applying for a job, I don't know, or light from a laser, you can turn portions of that photoconductor temporarily into conductors, so charge can move through them. And during that brief period, charge moves through the photoconductor from one side to the other. The positive and negatives can get together and they wipe each other out. They go to net charge 0. So light can erase this pattern of this vast array of one charge. You can erase parts of it. And then subsequently you stick toner to it. And I'll deal with that. I'm not going to do the whole rest of that story, because I've got to get other things done for today for the problem set. But you get the basic idea that you imagine a surface, you sprinkle charge on it, it attracts opposite charge to a metallized back surface, and then you selectively knock out charge by exposing the surface to light. And if you want a letter to appear here, the symbol T, for example, you wipe out all the charge except for right on that T area. You leave the charge there. You sprinkle toner on there. The toner sticks to the charge because it likes it. It's attracted by polarization effects, if nothing else. And now you've got a T. It used to be a pattern of charge that was T-shaped. Now it's a pattern of dust that's T-shaped. And you pick that up on a sheet of paper, and there it is, T. Okay? So, the big question I want to answer before leaving is, how do you get the charge on this layer of charge? How do you sprinkle it on there? How do you get that negative charge all over the surface of the photoconductor? And the way you do that is with a fine wire or a sharp point. And the reason a fine wire or sharp point does this is because fine wires have fine wires, if they have large voltages, large charges per large. I'm running out of time and I'm feeling pressure. Sorry about that. Something you've experienced. If you put a high voltage on a fine wire or a sharp point, around that fine wire or sharp point appears a very strong electric field. What's an electric field? An electric field is seemingly an artificial way of talking about the interaction between two charges. So let me do it this way. If I've got two positive charges near each other, up until this point I've talked about the left positive charge repelling the right positive charge directly. This one pushes that one away, and the right one pushes the left one away. They interact directly. That's the simple view of the forces between charges. There is an alternative way to look at the forces between charges. It's to say this first charge creates around it a structure in space known as an electric field. That electric field has a value and a direction at every point in space. It is strongest when you're near the positive charge, and it gets weaker with distance. Moreover, it points always away in the direction that a small positive test charge, so a little guy, if I put a little guy here and saw which way is it pushed, it's to your right. And if I put the little guy over here, which way is it pushed? To your left. And which way? Up. At every point in space, visualize an arrow, and if you watch the figure in the book, the electronic book, it'll show you the arrows. At every point in space, there is an arrow showing you which way a little test charge, a little positive test charge, will be pushed by this electric field. And so the electric field has a value at every point in space and a direction at every point in space. It's a vector field is what it's called. It's a complicated concept that it has values everywhere, each one having an amount and a direction. And it points in the direction that a positive charge will be pushed. So the electric field around this positive source charge is all away, points away, because positive charges hate positive charges. So the electric field is all pointing away. Around a negative charge, there's also an electric field, but it points in the other direction, toward the electric field. It points in the direction that test charges like to go, and test charges are always positive, so they like to go to negative charge. Okay, so there are electric fields. An electric field is a seemingly artificial way to look at how this charge pushes on that charge and vice versa. But it turns out electric fields aren't just a construct that's there for no reason. Electric fields, as we'll see, are real. They're actually there. They have a life of their own, and they push on stuff. And the electric field around a fine wire is extremely strong for reasons that I'll have to do next time. But it's so strong. The push on all positive charges is so strong in the vicinity of a sharp wire that it can push charges right out into passing air molecules. And so what's happening when I have a sharp wire like this near, either I put a lot of voltage on this or a lot of voltage nearby, in any case, I create a very strong electric field around that point. And it's so strong that it pushes charge right into the air, and the air begins to shuttle charges back and forth between these two surfaces, and it ruins that thing's ability to accumulate any negative charge. And in the case of a zero-graphic copier, it sprays charge onto a surface. So the zero-graphic copier has a fine corona wire in it, which you may have had to repair or clean somewhere in your past in dealing with your xerographic copier or your laser printer. Keeping the corona wire clean is important because it sprays charge by way of a very strong electric field onto the surface. And I'm hoping I've given you enough information to handle the problem set questions, and we'll continue on Wednesday.